I'd like to introduce Rob Norton, who's presenting today's webinar, Crop Nutrition, looking back on 2017 for guidance in 2018. I'm sure many of you know Rob. He's the Regional Director for the International Plant Nutrition Institute and has received many accolades for his work whilst at IPNI and in his previous workplace at the University of Melbourne, where he lectured and researched in agronomy for 30 years. Rob is currently also chair of our Extension Oz Crop Nutrition Community Practice, and we really appreciate Rob's input there. And today he's going to talk to us using information from the last season. So Rob, I am now going to give you presentation rights. It may take a minute. And I'll let you know when we can see your screen. It'll take a few seconds. Right, I've got your screen up, Rob. You're good to go.
Right, thanks, Luke. I appreciate the opportunity to give a talk on some of the issues that have come up and some of the guidance that we might be able to derive from those issues. And thanks for Extension Oz for facilitating this. I would make the point that while planning's important, I can't crystal ball gaze what 2018 is going to be. As you appreciate, we live in a variable environment. What happened last year and what happens next year are two different factors altogether. I also point out that most of you would be aware of the Extension Oz Crop Nutrition site website, and it is a great resource with timely information. The other thing that I'd point out about today is that it's National Agriculture Day, 21st of November, and you know, we are in a very fast-growing industry, Australia's fastest-growing industry, and you know, the moral is if you're fed and dressed today, you can thank a farmer for that, and we all really work for the farmers, no matter who's paying us. So what did I want to talk about? Well, the first thing to start off with is to think about what the season was like overall in 2017. There's a very famous cartoon that was in Punch over 120 years ago, which was about the curate's egg, and the bishop says that he thought you've got a bad egg, Mr. Jones, and the curate says, oh no, Lord, I assure you parts of it are excellent. And I think our season was also a bit like the curate's egg. It was good in places. ABARE estimates from the most recent crop report suggests that production will be down to about 36 million tonne. It's a 39% decline on what was an incredible record of nearly 60 million tonne of winter crop. Which was actually about 15 million tonne more than the previous record. So 2016-17 was a bottler for many people, for many growers, for agriculture in general, and 2017 has, you know, our 2017-18 has probably taken us back to 15-16 in terms of production. Victoria is in fact nearly twice what 15-16 production was, the estimates for this season. So if we look back on 2017, the map here is the Bureau of Meteorology rainfall deciles for the past 5 months from June to October, which is the general growing season, and we can see that just like the curate's egg, it certainly, the seasons were good in places. We had serious deficiencies, lowest on, very severe deficiencies, and even lowest on records, excuse me, in the mid-north of South Australia. So, you know, there were very severe conditions over much of the state, much of the southeast, and not so much into Western Australia, but certainly the rainfall deciles really show up in this mid-region. You know, we were hoping that in our region, in Victoria anyway, where the rainfall deciles weren't so bad in the lower southeast of South Australia, that we were in a good place. Unfortunately, the fat lady hadn't sung, and we had a couple of days of quite severe frost. The graph at the top is Westmere minimum temperatures, Westmere in Victoria, for the period of November, and basically we had very severe frosts over those 3 or 4 days, and maybe another one coming up on the final day. I've got the number at minus 2 degrees, which is a screen temperature value, and that's usually considered as a surface frost. And then in the Horsham, and that Westmere frost event coincided pretty much with the flowering of some wheat crops, and that's given a severe touch-up to those. And I know there's been several crops cut for hay down in that area. Here in the Wimmera, where I'm based, the temperatures also gave us quite a touch-up, particularly on lentils and chickpeas, which were just at this early potting and early seed fill stage, and losses from 30 to 100% are generally going around. So, you know, trying to give some general rules about what happens is not easy, because of the variation in some good crops, some failed crops, some crops that grew well but then won't have any grain yield. So what we do about thinking about this is we really need to think and learn from the past. You know, 2017, you know, what's done is done. Frosts have been, the droughts have been. 2017 was different to 2016. 2018 will be different again. And we can't just hope that we get another 2016, because hope is not a strategy. We need to have a plan in place in terms of crop production, but in this case, I'd particularly like to refer to the aspect of nutrient management, which is really one part of the whole farm management cycle, crop management cycle. We can divide that management up into two parts: strategic and tactical management. And strategic, I think, are things about managing approaches for nutrients where there's little to no other option for intervention. So they're things we would need to do it at or before seeding, and maybe in the context of a longer objective, such as raising soil test levels or addressing acidity with lime or acidicity with gypsum. And that might be something over a 3 to 5 year period or even longer. And we would have to be planning that at the start of the season, well actually now, because it's now is when most of the growers are seeing most of their paddocks. This is when they're out harvesting, seeing what's happening with yield maps, etc., and getting a feeling for what's happening in the field. Those strategic decisions are usually around phosphorus, but also around potassium and zinc and copper, particularly phosphorus. I'll put potassium in brackets because, in fact, the effectiveness of interventions with potassium is higher if it's done at seeding rather than done as a tactical approach. And zinc and copper too, depending on the situation, may in fact be more effective with a strategic approach, a long-term strategic approach. And I know many growers use low rates of zinc and copper just as a top-up to ensure that their levels don't decline. In terms of the tactical approach, this is where interventions can be implemented in season. And it doesn't mean we don't plan them now, but we plan them at the start of the season, plan to be implemented at the start of the season. And we are because of nutrients like nitrogen, sulfur, etc., being able to be top-dressed and be effective, we can modify that process during the season. And the normal nitrogen strategy is to follow yield levels and adjust nutrient inputs accordingly. So I've used Donald Rumsfeld many times in terms of explaining, this approach, and in particular in this case, I'm going to talk about the strategic approach to nutrients, which particularly is phosphorus and nitrogen and potassium. What do we know? Well, Rumsfeld talked about known knowns, known unknowns, and unknown unknowns. And the known knowns for us in terms of this year's, for next year's crop really are, we know what's been removed. Every grower, nearly every grower would have a yield map, such as the one in the bottom right corner of the screen. And so we would have a spatial view. Even if they don't have a yield map, they would certainly know how many truckloads of grain came out of the paddock. We may also know some nutrient concentrations, such as protein content in canola and also in cereals. And so we do know a little bit already about what's happened, so what the removals of nutrients were. We can also know, if we go and take some soil samples, we know what the likely nutrient supply is, and that's where we're soil testing or soil guessing sometimes, based on history, looking at using a proof soil test to get some value, to get some assessment of where we are. And then we think about the known unknowns. The big unknown for next year is what's the demand for the nutrients in the next crop, and what are the likely losses of the supplied nutrients because of the seasonal conditions or the soil conditions. Now, both of those are known unknowns. Experience helps us transfer some of those known unknowns into our known knowns, so we can have, use models to look at what potential yield demands are. We've got access to soil probes to give us ideas about soil water content. But really, we actually have very little capacity to deal with the unknown unknowns, simply because we don't know what we don't know. And so with nutrients, obviously the first and most important thing to think about is removal and soil testing. If we just consider, in terms of removal, what's going out the gate, that obviously depends on yield and management. And the table that I've put on here is an example for a 5 tonne, 12% protein wheat crop in terms of the amount of nutrient that would go out the gate in terms of nitrogen, phosphorus, potassium and sulfur. Canola, 3 tonne canola crop is pretty similar to a wheat crop, a 5 tonne wheat crop. One of the big differences is the higher sulfur removal in the canola crop. Barley is very similar to the cereals, maybe a little bit more potassium, but not a great deal difference. Those guys who had frosted crops that cut them for hay will find that probably a 5 tonne crop is probably a 9 tonne per hectare hay crop, and the nitrogen going out the gate is quite a bit higher. Phosphorus is pretty similar. Potassium is an order of magnitude higher, and sulfur is quite a bit higher as well. And that's because what we have is that we have the grain plus the stubble, and that stubble, that 160 is really the sum of that wheat plus the stubble content to get that 160. The point is that where we're thinking about hay crops, we're running a lot of potassium out. And if we're burning stubble, we'll also lose nutrients. We'll lose maybe all the 46 kilograms of nitrogen, a lot of potassium, a bit of sulfur, and not very much phosphorus. The amount lost will depend on the weather conditions around that between when the stubble's harvested and burned. If it's wetted and a lot of the phosphorus and a lot of the potassium will leach out, as will some of the nitrogen. So those losses may in fact be smaller. Again, without a crystal ball, I can't tell you how much less they would be. What we do know about those values, though, for grains is that grain mineral contents are quite variable. So even though we might say for wheat that it's 3 kilograms of phosphorus per tonne of wheat grain, the blue line on this frequency graph is an indication of the range of phosphorus contents we measured in some grains which were derived from NVT experiments. over a couple of years, and the median value was 3.5 kilograms of phosphorus per tonne on a dry grain basis, and the range was from 1800 or 1.8 kilograms to 4.5 kilograms per tonne. So very large variation in the concentration of grain. And if you're really looking at doing nutrient budgeting, then getting actual removals by having some grain analysis is a very good strategy. Now, phosphorus is probably the major decision that we'd be thinking about now, and so the first part of that phosphorus decision is about removal. And removal depends largely on yield. So a 5-tonne wheat crop, as we've just said, 100 kilograms of nitrogen, 15 kilograms of phosphorus, 18 kilograms of potassium going out the gate, or that 9-tonne hay crop that was cut from maybe a frosted wheat crop, 160 kilograms of nitrogen, 15 kilograms of phosphorus, and 180 kilograms of potassium going out the gate. If that yield of the cereal crops only is 1.5 tonnes per hectare, then the amount going out the gate is proportionately less. So 30 kilograms of nitrogen, 4.5 kilograms of phosphorus, 10 kilograms of potassium. And so in terms of phosphorus, if the phosphorus removed, it either has to come from soil supplies and or from the fertiliser inputs. So to balance those nutrient removals in those three examples, for the 5-tonne wheat crop, to replace what was removed, we'd be looking at 75 kilograms of MAP, 200 of urea, 40 kilograms of MOP. If that crop was cut for hay, it's 75 kilograms of MAP, 320 kilograms of urea, and about 350 kilograms of muriate of potash. If we compare the 5-tonne and the 1.5-tonne crop, the proportionate demand then, or the proportionate demand to replace the nutrients also declines. So it's about 25 kilograms per hectare of MAP and 60 kilograms of urea. So that's the removal part. The other part about a phosphorus decision is the soil supply. In a soil, for any particular soil, the total phosphorus concentration may be 500 parts per million milligrams per kilogram, so that equates to 600 kilograms per hectare of phosphorus. But very little of that is available, and we measure that in terms of coal phosphorus, standard phosphorus test, and a coal phosphorus test value of 40 equates to about 50 kilograms of phosphorus per hectare, which still sounds like a lot. Now, some of that phosphorus is actually, in fact, most of that phosphorus is actually cycling through organic forms. 20 to 80% of the total phosphorus in the soil is present in organic forms, and it, like nitrogen, needs to be mineralised to be released into the soil solution, which is where the plants, the crops, will access that immediately available phosphorus. There are other pools of phosphorus which are also accessible, which is where the phosphorus is adsorbed onto surface part of soil particles. And then there are other pools where there's low or very low accessibility, where the phosphorus is either strongly bonded or absorbed into soil particles, or precipitated as phosphorus-containing minerals with very low solubility. So if we have the intervention of adding a fertiliser which contains soluble P, soluble phosphorus, and water-soluble phosphorus, there's also a small amount of citrate-soluble phosphorus, but we'll deal with the water-soluble phosphate first. In terms of what happens to that, about 25% or less of that water-soluble phosphorus ends up in these pools, in these available pools, and then accessed by the plant. You hear all the time that there's very little fertiliser phosphorus that's taken up. It's actually most comes from the soil, and that's true. But this other 75% or more of the applied phosphorus ends up in these lower availability pools. Eventually, that material will come back into these higher availability pools, but it will take some time. And PBI, phosphorus buffering index, changes this in some ways, changes this balance of available, how much is taken up and how much is moved into the low availability pool. In high PBI soils, much of the applied phosphorus enters the lower availability pool, so it goes to this side. And that's because it's tied up in acid soils with iron and aluminium phosphates, or in alkaline soils with calcium phosphates. And in that situation, both of those form insoluble, precipitated or surface bonded phosphorus sources. This can bleed back into the surface absorbed and then into the soil solution and then into the plant. But the size of this pool needs to be quite big, and in some cases some of this material may be actually precipitated and not available at all. If you look over the long term, the experiments we've had here with a 19-year fertiliser experiment showed that in fact the recovery of phosphorus applied to mixed cropping rotation in the Wimmera, around about 85% of the phosphorus applied was recovered in the grain. When we applied 9 kilograms of phosphorus per year, basically the crop balanced off with that removal. So even though we might say that 25% of the phosphorus is removed, in fact in the longer term this backup is supplying phosphorus to the crop, and you can't really distinguish between those either of those sides, because this low availability side of the program gets moved into the more available side in many cases. So we come to soil testing, and soil testing gives us an estimate of soil P supply, and this is the typical sort of response curve on the vertical axis of relative yield, 100% through to nil, and the soil test level, whatever the soil test level is. And they're defined usually in terms of a critical range, which is a range between, usually between, some would say 95 or 100%, or 90 and 100% of that yield potential. And this is the range that you get out of the Better Fertiliser Decisions for Crops program. What those ranges tell us is a little bit about the strategy for managing phosphorus within those critical ranges, or around those critical ranges. If the values are in this lower range, what we'd be looking at is trying to increase the soil test value. We'd be looking at replacement of what's being removed, and we'd also have this sort of phosphorus tax in what's being fixed in the soil. That soil fixation will depend on PBI, as will this capacity to increase the soil test. As we move into this critical range, we've already got the soil test value to where we want. So we're really looking at replacement value plus any losses due to soil fixation, and maybe also in all cases, any soil erosion where the particulate phosphorus is removed. And most people would think about their phosphorus phosphorus management in terms of this replacement value. If we're above the critical range, then the strategy would be to try and get that value from down into the critical range because we have a whole resource here that's not being effectively exploited. And so we'd be maybe looking at applying less than replacement to draw down on the soil supply. And I think that's something that many growers need to look at. And we'll come back to that towards the end with some data that I can present to you. In terms of critical coal P values, these are the values taken from the Better Fertiliser Decisions for Crops project, which is the repository of fertiliser response information that's able to be interrogated, and the table here is taken from a paper by Bell et al. In 2013, which compiled some of these into the crop, the soil type, the critical values, and the critical range. And the critical value is for 90% of relative yield. The magic numbers are there. That gives you where you're sitting in terms of whether you're at sufficiency or whether you're at maintenance or whether you need to build soil tests. The other thing that this table tells us is something about where we would think about allocating phosphorus. Canola has a lower critical soil test value generally than cereals, and that tells us that canola is more able to effectively scavenge phosphorus in the soil. And so it's less responsive to phosphorus than cereals, whereas something like peas is probably about the same response, maybe a little, probably pretty much the same as phosphorus. So if we were thinking about allocating phosphorus, we may consider putting less on canola and relatively more on wheat and peas. And the benefit extra benefit we get from the legumes, peas just being an example of a legume, is the response in terms of biomass and therefore fixed nitrogen where there's extra phosphorus applied. The other interesting work that's come out of the Better Ferts program is that wheat after canola tends to be more responsive to phosphorus. And I'll put a question mark there because the data has been developed and published, but I think we still need a little bit more confirmation of that with some more research. So knowing those critical values, knowing how we manage them, what's the current situation in terms of topsoil coal phosphorus values? This is some information that Incitec Pivot through their Nutrient Advantage Lab kindly supplied a couple of years ago, looking at cropping topsoil coal phosphorus in Victoria over 2008-2014, and they're the samples that went through their labs. And the different colours are, the yellow or the mustard colour is coal peas below 35 milligrams per kilogram. So we'd say that they're coal peas that may in fact be responsive. The purple line at the top are coal peas 35 to 70, the green 70 to 140, and the blue 140 milligrams per kilogram of coal pea or more. Now I suppose the sobering point about this is that if you break that down to regions, in the southwest of our state, only 22% of cropping soils have coal peas that would be in the responsive range. So that those guys are actually operating in the area where they could reduce inputs. The other aspect is that in the north and northwest, there's quite a large, very much higher proportion of paddocks coming back with responsive coal values, and the central Victorian area, it's very much like the southwest. So there are, even so in the north and northwest, even though we have a relatively high proportion of paddocks, there's still 4 out of 10 paddocks that have coal P values that indicate that they would not respond to additional phosphorus fertiliser. So what do we do about that? Well, we think about where we are in this overall response curve, and we would go to maybe a starter only or zero fertiliser if we've got those high soil test values. So if those high soil test values are above critical, why would we put any phosphorus on at all? Well, over the years, it's been consistently shown that the positional availability of phosphorus is very important. Having access to fresh phosphorus early in the season is important for crops. Phosphorus is immobile, so it virtually stays where you put it in most soils, and so the roots will proliferate around that phosphorus band. Whereas for nitrogen, nitrogen will plume down. It will still remain in a band, say if it's mid-row banded, but the roots can chase the nitrogen. So roots need to access that phosphorus. If they do, they proliferate, and that helps with general crop development. An example of this was from the 2006 drought in the Wimmera, where an experiment was undertaken looking at 0 and 10 and 20. And what happened if you applied none, 5, 10 or 20 kilograms of phosphorus? Or where you applied no phosphorus, there was still some carryover of the 20. Where you applied 10 kilograms, there was still a carryover. Where you had 5 kilograms, so a small amount, small amount of phosphorus applied in the subsequent year, then that phosphorus content was able to support a yield up to what was equivalent of the previous year's 20 kilograms. So there's always seems to be some benefit, even with high soil test values. At the long-term experiment I mentioned, over all soil test values, and that was coals up to 100, there was a benefit between 0.15 and 0.25 tonnes per hectare in grain yield, in wheat yield, where phosphorus was supplied at seeding. The minimum amount, though, is probably in the range of 3 to 5 kilograms per hectare, and to supply 2 kilograms of phosphorus in 25 centimetre rows, that would mean that the granules are about 8 to 12 centimetres apart. It doesn't matter whether that's MAP, TSP, or DAP. Those granules will be, almost as far apart as your roots will be between the drill rows. So if you go any lower than that, accessibility of those granules, of the roots of the granules, is significantly diminished. It's always good to get confirmation that phosphorus is still important, even though there's those soil test values, and this is the main picture here is from Craig Drum at Tattyoon, showing really nice response where there was a fertiliser blockage with the MAP. In canola, very clear difference there, so phosphorus is still important. And another nice picture from Matt Whitney in the Mallee, where there was a blocked fertiliser row here. And again, that shows you how close the fertiliser needs to be accessible to the crop, as well as the impact of no phosphorus. So it's still important. Balancing input and output, we need to know where we are in terms of the soil test. So what about nitrogen? Well, there's 3 things to mention about nitrogen. The first is the legume influences from 2017. The amount that a crop fixes, a legume crop fixes, depends on a couple of things. The first is this nice little graph, which is the soil nitrogen, nitrate nitrogen at crop establishment versus the amount of nitrogen fixed by that crop. And basically, if there's a large amount of nitrogen present in the soil, the legume crop doesn't want to waste energy to fix nitrogen. It will progressively decrease the amount of nitrogen fixed by its nodules. So the second part is the amount of growth, and therefore also the amount of yield. And fixation and yield, obviously the crop fixes, but we also, with a legume crop, we also remove that nitrogen in the grain. And this is a nice little example from Michael Moody in the Mallee, looking at end fixation along the x-axis, and on the y-axis is how much is actually fixed into the next crop. And basically, there's different crops seen here. Faba beans were sort of the star performer in terms of the amount fixed, but really only half the nitrogen fixed ended up into the subsequent crop. So high-yielding legume crops are also fix a lot of nitrogen, but a lot of that nitrogen that's fixed is removed, and there's variation among legumes, with lentils and chickpeas being at the lower end of the fixing scheme, and field faba beans being the upper end, faba beans and lupins. The third factor is about inoculation effectiveness and soil pH. We had some experiments down at Glen Thompson looking at potassium, and we had field beans, canola and wheat, and this is the effective nodulation we had on those beans due to the fact that the soil pH was around 5. So there was really no effective nodulation at all in this situation. So the end fixation would actually be effectively nil. So these crops are net nitrogen users, significantly net nitrogen users. So those three factors help us think through nitrogen influences. So how those scenarios going to play out in 2018? Well, again, I can't give you a crystal ball and put all those things together, but in terms of a concept about ranking paddocks in terms of their likely nitrogen availability, the highest are likely to be failed faba bean crops due to frost and disease. That's likely to have the most nitrogen available. Good bean crops are likely to have still, even though the yields are high, still likely to fix a lot of nitrogen. And then as you go down, failed lentil crops due to frost. If they're a failed pulse crop due to drought, they probably didn't grow much anyway, so there was not much nitrogen fixed. And then we go into canola crops, good canola crops, good wheat crops cut for hay, and good wheat crops cut for grain. So I can't tell you how many kilograms it would be, but that's about the ranking of the paddocks. There's some interesting work here about canola crops seeming to preserve some nitrogen from one season to the next, so that canola, wheat that's grown on canola tends to be able to access relatively more nitrogen, because the roots of canola have some inhibitory chemicals which reduce the rate, which are effectively nitrification inhibitors. And so canola crops are likely to have wheat growing on after canola crops is likely to have a lower nitrogen requirement because some of the nitrogen's carried through. It's the processes from now that will determine how much of that nitrogen carries through to our seeding. To seeding, that's obviously all those processes that affect both mineralisation and immobilisation, and we've got rainfall and temperature, of course. Crop residue management, whether you burn, bash or bury or bale, and also what the rainfall and what your weed control program is in terms of those weeds exploiting the nitrogen and the water. So the processes from now will determine the nitrogen status at seeding. So how much do we need then at seeding? Well, if there's 30 to 50 kilograms at seeding, that's probably enough to get through, and that's in the whole profile. It's interesting that the figure up in the right, top right of the screen is some work that Glenn McDonald summarised looking at the yield response with nitrogen at sowing versus the yield response with nitrogen at GS30, and it actually works out to be almost a straight line. So there was no particular difference between top-dressed in-crop nitrogen and that seeding nitrogen. And in fact, I've sort of been making the observation that rate is in fact more important than timing and source, provided we have enough nitrogen at seeding to get us through. And in a lot of cases, we would have that. The only issues, there are a couple of issues with nitrogen at seeding, and nitrogen at seeding is the time when we know least about our yield potential and when we have the highest seasonal risk, the highest unknown risk of how the season's going to play out. So putting all your eggs up front is not a really good strategy. There's also potential for seedling damage if there's high rates of nitrogen placed in furrow. And one of the interesting areas that Graham Sandrill's been working on in New South Wales is looking at mid-row, skip row banding of urea as a way to get high rates of nitrogen in its seeding, but keeping it away from plant roots. The other aspect about seeding versus later application is how many opportunities are there for in-crop application. In the lower rainfall and even in the very high rainfall areas, the number of times when we can get on fields and the number of times we can get rainfall events to wash nitrogen in tends to be limited. So if we think about those factors, we may decide to have more nitrogen at seeding, and probably this year on big crops, anywhere there's been big crops or cut for hay, it may be important to have more nitrogen at seeding, but the thing is to soil test. The other aspect is to, I think, is to use a nitrogen-rich strip. Most of you will know I've been banging on about this for a long time, but it is a way of making estimates of mineralisation and denitrification and leaching in your field across a landscape, and you're able to monitor what's going on in those paddocks. And the thing about them is interesting comment by Mark Branson from South Australia, saying that it actually allows him to decide when he doesn't need nitrogen, and he says that's the aspect that saved him more dollars over the year, is where these processes are running pretty well. The other aspect about application is making sure you get the application of the fertiliser right. Application evenness, if you're putting fertiliser on, the last thing you want to see is stripping in the paddocks, and this is pretty obvious that the fertiliser spreader's not been set up to the right bout width. But we also see it in the lower picture, even when the spreading pattern is pretty awful, really. And we saw this in a couple of fields where this year where there was high nitrogen demand. So it 2017 with high nitrogen demand, where it really played out as areas that didn't have very good spreading showing up. So using AccuSpread and FertCare become quite important, FertCare accredited spreaders, to make sure they're able to spread to the widths they advise. Just a couple of things about potassium and a couple of the other nutrients. Be aware of potassium deficiency. The sort of key areas are light sandy soils, high rainfall, and where hay cutting has occurred, and you saw the figures there of a 10-fold increase in potassium removal for a wet crop that's cut for hay versus one that's stripped for grain. You can look for the diagnostics such as that patches, the urine patches. You look for windrow effects where there's better growth in the windrows, and you might even consider trying a potassium-rich strip. 50 kilograms at least at seeding. Potassium and sulfur are both macronutrients. They behave quite differently. Potassium behaves more like phosphorus. It's not very mobile. Sulfur behaves more like nitrogen, and so the fundamental principles of potassium and sulfur management become: sulfur is more like nitrogen, which we would manage tactically. Potassium is something we would manage like phosphorus. We would manage that strategically. So although we might like to think of potassium as being soluble and easily accessible, it does get bound up on the soil colloids, and particularly on heavier soils will have low mobility. Final word about the micronutrients. The conditions at which they become more or less available are determined by a whole range of soil conditions, such as obviously soil pH, we all know about, but waterlogging or drought. Drought restricts root growth, which then restricts the capacity for the crop to access some of these micronutrients. High organic matter soils will reduce the availability, particularly of copper, but increase the availability of zinc, because the zinc is more easily mobilised, is more easily mineralised in those processes. Phosphorus content can affect the availability of some of these micronutrients, as can the soil texture, as can compaction. So, you know, these are the things that will play out in the season to come, and it's worth just keeping an eye on some of those micronutrient conditions if it becomes waterlogged or drought, and particularly on specific soil types. Just finally, it's not all about nitrogen and phosphorus alone. We really need to consider balanced nutrition. I just want to go quickly through one experiment we had in 2016 at Bull Lagoon in South Australia, which was a canola crop. This is what the site looked like. So it was a little wet. I think it was actually in Bull Lagoon, not near Bull Lagoon. The yields in the end, top yields were 3.5 tonne of canola, and the two sets of bars you can see there are where we put 60 kilograms of nitrogen or 30 kilograms of nitrogen with all the nutrients applied. So we gave it the Rolls-Royce of fertilisers, treatments, and then if we put no fertiliser on, and the difference between those is the response to fertiliser. You can also see is where there was low nitrogen, there was very little extra response. So nitrogen in some ways was driving the ability of this crop to express its yield potential. If we took and looked at the 60 kilograms of nitrogen treatments and then dropped out phosphorus or potassium or sulfur or the trace elements, what we see is that there was a significant decline in, there was no real significant difference in any of those nutrients. The phosphorus level was declined a little, but it wasn't a significant difference. The others were all pretty much on par with where we supplied them all. So if you looked at that, you would conclude that there was no need for phosphorus. If you then put more nitrogen on, this time 100 kilograms of N, 100% of N, in fact the differences become expressed quite significantly. So we have the situation here, we have the situation here where you have an adequate N supply to meet the water limited yield potential. In fact, where there was no phosphorus, the crop was in fact phosphorus deficient, and so the difference there is about 25% if you added phosphorus between this blue bar and the blue bar at the 100 at the all. And the other thing we saw was that sulfur actually also fell out as being something that was limited in supply. So if we dropped the sulfur out of the fertiliser program, it led to about a 15% yield decline. But those only occurred when we had a high level of nitrogen. So that's where this interaction between nutrients becomes important, and pushing towards the most limiting factor. And in a lot of cases, nitrogen is very important, and we would like to make sure that water becomes the limiting aspect, not nitrogen or phosphorus or sulfur, any of the nutrients. And just a final comment about a survey I did with Southern Farming Systems, supported by GRDC, which we looked at 500 paddocks over 3 to 5 years from Victorian and southern New South Wales. And we estimated the amount of nutrient that was going in and the amount of nutrient that was being removed in grain and hay or however else being removed. We took account of fixed nitrogen, and the graph here, the blue graph, is for nitrogen, and the measure that we have is what's called the partial nutrient balance. So that's the amount of nutrient going in to the amount of nutrient going out. So at 1, that means there's as much nutrient being removed as being supplied. As we go higher in those values, so 2, for example, means that there's twice as much nutrient being removed as being applied. And 15% of fields, 15% of those paddocks over 5 years had twice as much nitrogen removed as being supplied. And that's coming from mineralised organic matter. And in fact, 60% of those fields were in mining nitrogen, effectively mining nitrogen out of the soil. That's a challenge, to work out farming systems that will reduce that mining. The other aspect was with phosphorus, and in some ways it was almost the reverse, where we had our partial nutrient balance, the amount of phosphorus removed versus supplied. Only 15% of fields were mining phosphorus, and about a quarter of the fields were in fact removing twice the amount of phosphorus. So they were applying twice the amount of phosphorus that was being removed. Now, there's certainly soil fixation there, but the question is, with these 2 graphs, would you be thinking about substituting some of your fertiliser phosphorus budget for your fertiliser nitrogen budget? So with that, I'll finish and just do a quick summary about our strategies. Well, it's obviously soil test and do a nitrogen budget, no surprises there. Invest in nitrogen early, between DC30 and 55. Take a short-term view or a tactical view with nitrogen. Fix nitrogen on failed legumes. It's hard to see a bonus, but that may be a bonus, the only bonus we get from those crops. Phosphorus at sowing is the only real option. Banded placement near the seed row is a really important strategy for phosphorus. We should be taking a long-term strategic view, adjusting rates to offtake, plus a tip if the soil test's above or critical, at or above critical, and have some phosphorus at sowing. We'd be trying to keep an eye on potassium and sulfur, especially potassium with hay removal. So with that, Luke, I'll conclude and invite any questions that might come along.